All right, guys, here we go. Here we go, guys. So a lot of this stuff you're going to see, hopefully a lot of this is review for you guys through physics, because in physics there's always something in motion. So that's why a lot of this is going to overlap and be review, hopefully. So now you know what an instantaneous rate of change is. It's just literally an instantaneous rate of change. It's a slope. Cool. So I can find an instantaneous rate of change for anything if they are related in some way. Yay or nay? Yay. All right. So as long as they're related in some way, it doesn't have to be with respect to time. It can be with respect to anything as long as they're related. Chavez, you're confusing me as soon as you said that it can't be with respect to time. So look at example 1. It says find the rate of change of area of a circle with respect to its radius r. So is area, first and foremost, is area and radius related? Yes, they're related by what? Area equals pi r squared. It said area, right? Okay, so when it says find the rate of change of area with respect to radius r, so this is the algebra. We're not doing calculus yet. So that means they want a change of area over a change of radius. That's algebra. That's not calculus. So if someone told you, what is my radius what is my area when the radius is 2? You would calculate, you would plug in a 2, find the area. What is my area when my radius is 3? You would put a 3, and then you find your area. And if someone tells you, what is the rate of change between r equals 2 and r equals 3? That's an average rate of change, not an instantaneous. Then you would do your area at 3 minus your area at 2 divided by 3 minus 2. Does that make sense?
Yes.
Okay. Now this is calculus. They want an instantaneous rate of change. I know it says, it doesn't say instantaneous. When it says find the rate of change of area of a circle with respect to its radius r, they're assuming instantaneous rate of change. Cool? So here's how you do it. I'm going to be taking the derivative of area with respect to r. So I'm going to write dA dr is equal to, what's the derivative of pi r squared? Perfect. I heard someone say it. Pretend r is like an x. 2 pi r. Done.
Wait, so you treat pi like an additional variable?
No, pi is a constant.
Oh.
It's
okay.
r.
So like it's the 2 pi. Okay.
It's the r, right? Okay. So I just brought the 2 to the front, 2 pi r, and that's it. Cool or not cool?
Cool.
And I guess technically, don't write this down, just listen. It's going to help for chain rule or for related rates. Really, I should be putting dr, but dr is just 1. So maybe I shouldn't have even mentioned that because it's just going to confuse you. All I did was take the derivative of area with respect to what? Radius. There it is. Done. And that was it. Cool? All right, letter B. Evaluate the rate of change A at r equals 5 and r equals 10. I guess better language would have been evaluate the instantaneous rate of change A when r is 5 and when r is 10, but that's fine. All right, so here it is. Here's how you say it. dA dr, and you write a line like so. That means evaluate at r equals 5. This is how you do it formally. If you don't put that line, it's okay. They're not going to take points off. But, when you're discussing mathematics, technical mathematics, you want to be specific. So this means, what does that line mean? Evaluated. So for you computer scientists, you're going to be doing the same thing. You're going to be programming, and you're going to be putting a line, literally, in Java or C++, C. You'll see what I'm talking about when you guys start programming. And you're going to go 2 times pi times 5. And that is 10 pi. And there are units. We'll talk about the units in a little bit. Here we go. dA dr when r equals 10 is equal to 2 times pi times 10. And that is 20 pi. And there are units, but we'll talk about the units coming up next. Here we go. Letter C. If r is measured in inches and A is measured in square inches, what units would be appropriate for dA dr? What do you guys think? Don't be robots. What is area? What they just told me. Area is measured in what? Inches squared.
Inches squared over inches.
Perfect. Do not cancel. Because if you cancel, then it just becomes inches, and that's not what we want. So this is square inches. If you want to write it in words, square inches per inch of radius There it is in words. How it is with just units, square inches per inch.
Oh, because basically what we found was slope, right?
Yeah, we found how fast the area is increasing per inch of radius.
So if the area increases, or no, if the radius increases.
So does yeah. So in just plain English class, it's square inches per inch of radius, or square inches per inch of, yeah, well, I said the same thing. So in units, square inches, line / per inch. Do not cancel. Cool? Cool. All right.
So it would be 10 pi inches squared over inches.
10 pi square inches per inch. And 20 pi square inches per inch. All right. All that stuff in the next page is just fancy talk, just fancy symbols. Usually they use S for position. Here it is. Usually, not always. Sometimes they use X to indicate it's traveling on the x-axis.
Yeah, because we use X and Y. Like we
Yeah.
always, for displacement, we put change in X.
Yeah.
But then
For
Academy did like S.
yeah, same. Yeah. So now you're seeing what's up. So the S is not the only. If it's motion on the x-axis, they usually use X. If it's motion on the y-axis, you use Y. Cool or not cool? Okay. And I guess I should write X of t and Y of t, and then put what each one means. Motion on x-axis.
Oh, okay.
Motion on y-axis. We're not in multivariable calculus yet or BC yet. When you're in BC calculus, you'll be doing two-dimensional motion. And then when you take multivariable calculus, Cal 3, you'll do X, Y, and Z motion. And then for this is general. If they don't necessarily tell you that it's moving on the X or Y axis, they'll just give you a general equation. And they'll use S. Cool? All right. So the derivative of position will give you velocity.
Because the slope on a position times X. Yeah.
That's right. That's it. That's all it is. So that's why when you had physics last year, you probably didn't do any other curves other than linear curves. I don't think you've had, well, yeah, maybe you've had something where you analyze the velocity acceleration, but as far as like to calculate distances and slopes, they're probably all linear in physics, no? Yeah, so now with calculus, we can do any curve. It doesn't have to be linear. It can be anything. So here we go. This is just a definition. Absolute value of velocity is speed, because speed does not have direction. Speed is a scalar. And velocity is a vector. And then this you already know. This means here that dv dt literally means derivative of velocity. Of velocity. So they're telling you that the derivative of velocity is acceleration, which we already know. And then this right here, d squared s dt squared, that means second derivative of what? Second derivative of position. Yeah, so think.
Oh, that makes sense.
All right, let's slow down.
Is the second derivative of position.
Yes.
Wow. Okay.
So let's slow down. If they give you a general position equation, S of t or whatever, f of t here, they're saying S equals f of t. So the first derivative is velocity. So if they give you a position, the first derivative is velocity. Now with respect to position, if I take the derivative again of velocity, what's the derivative of velocity? The derivative of velocity. Acceleration. But with respect to position, it is the second derivative. Do you see how they're connected? So y prime, y prime prime. If y is your s of t, your position, then y prime is your velocity, then y prime prime is your acceleration. Do we know what we're saying? Okay. Yeah, here. If y equals position, then y prime equals velocity, and then y prime prime equals acceleration.
Literally, we're like right in parallel in physics. That's very just in free fall.
Are we still okay? Okay. Then here are some free fall constants. If you're up in the mountain, it's probably going to be a little less. If you're at sea level, it's probably going to be pretty close to this. It doesn't vary much because, we're all here. Earth is way bigger than... so it's going to be these values that we use. These come from somewhere. They don't just magically appear. They came from this right here. And I don't think it's exactly 32 feet per second per second. If you go to Google, you can find the exact amount. And I don't think it's exactly 9.8 meters per second per second. Yeah, I don't remember. It varies slightly, right? If you're in a mountain, you're lighter. If you're below sea level, maybe you're heavier. I don't know. Okay. Are we cool right now? Okay. So let's see. I think we know enough to start with our first one here. Example 2. Ready? A dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second. And then I gave you the miles per hour there. It reaches a height of s equals 160t minus 16t squared feet after t seconds. If you were in physics 1, they would probably call this initial velocity. And you would probably... So this equation came from somewhere. Where did it come from? It came from, let's see, how do you physics 1 people know it? You probably know it as delta x equals velocity initial times time plus 1/2 at squared. Okay. So that's my equation. That's where this equation came from. Notice it has s. It doesn't have x or y. S is used for general purposes. So look, 160. Well, look, that's your initial velocity. And then why is there a negative instead of a plus? Because acceleration due to gravity is going in the opposite direction. So we're using 32 feet per second per second. Half of 32 is 16. So there it is. This equation did not just magically appear. It was derived from just the laws of motion. Cool or not cool? Cool. So now it says, how high does the rock go? All right, so here we go. Ready? We just have to use a little bit of logic. When I throw this pen up, no, I'm not going to throw it at anyone. When I throw this pen up, I want to know how high it goes. Well, when it reaches its highest point, what is the velocity at that moment? Zero. So what I'm going to do is I'm going to find a derivative of this position. That's going to give me my velocity equation. And I'm going to equal that velocity equation to zero. So here we go. I'm going to go, let's see, velocity equals, and I'm going to write s prime. So you guys know that I'm taking the derivative of position here. Equals, what's the derivative of 160t with respect to t? 160 minus, what's the derivative of 16t squared with respect to t? 32t. Now, if you want to put somewhere on the side here, s prime means a derivative, but I'm doing it with respect to time, so I'm going to write ds dt. So you know that you're taking derivative with respect to t. Cool? All right. Here we go. What am I going to equal this to? 0. So then I'm going to write 32t equals 160. I hope that doesn't confuse anyone. Okay, I can see. Okay, I'll stop. I'll just do 160 equals 32t. There, now no one's offended. Because I like to, okay, but it doesn't matter. I'm going to solve for t. So divide by 32, divide by 32. So t equals what? I don't know. Let's take a calculator. Is it 5?
Yeah.
All right. T equals 5. Now that I know that it takes 5 seconds for me to have a velocity of 0, I'm going to plug that in back to what? The original. So my position at 5 is equal to 160 times 5 minus 60 times 5 squared. And this is going to give me the height that it went. So I take my calculator, second quit, and I'm going to go 160 times 5 minus 16 times 5. Is it 5 squared?
Yes.
Enter. And I get 400. And I need units. 400 what? Feet. Usually you want to answer the question with a sentence. So So when it says how high does the rock go, you want to say the rock goes 400 feet. The rock goes 400 feet high or whatever. But there it is. I think that's good enough. Even if you were to not write a statement, I think you would get credit for this. What's up, miss?
So to make sure we're finding, we just found the position, right?
The position at 5.
The position.
Because at 5, that's how long it took for this rock to reach its highest point. At the highest point, the velocity was 0
Wait, 5 what?
seconds.
So anytime you're finding the position, you just find the derivative.
No, it depends on what they're asking. They're asking for how high it went. So what do I know? I know that whenever this rock reaches its highest point, I know the velocity is 0. So because I need the velocity, I took the derivative.
Okay.
You know what I mean? Yes.
So if you want to find acceleration, you need derivative.
Of velocity, of the expression. Yeah. So next letter, it says, what is the velocity and speed of the rock when it is 256 feet above the ground on the way up, on the way down? Okay. So I need to figure out a time when you're 256 feet on the way up and on the way down. Cool? So what I'm going to do is I'm going to set my expression, S of t, equal to 256. So here we are. I'm going to go, does everyone know why I'm doing that? Okay, I'll stop again. It says, what is the velocity and speed of the rock 256 feet above on the way up and on the way down? So I need a time. So how do I get my time? I have a position equation. So I'm going to equal my position equation to 256 to see the times that I'm going to get when I'm on the way up and when I'm on the way down. 256 is the position. So we're assuming that this is like a cannon that is propelled just straight upward. See, it says straight up. So it's moving on the y-axis only. So here we go. I'm going to write 160t minus 16t squared equals 256. I like to work with positive numbers and positive numbers only. So instead of moving the 256 to the left, I'm going to move the 16t squared and the 160t to the right. So I'm going to rewrite it like this. 16t squared plus, minus 160t plus 256 equals 0. Are we still okay? 16, I got a hint. I feel 95% confident that, yeah, it does, I think it's 16 squared. 16 goes into 160 for sure, and I believe it also goes into 256. So let's factor out the 16. Parenthesis t squared minus, is that 10t? Plus, is 16 squared 256? I want to say it is. I'll check just in case. 16 squared. Yep, we're good. We're good. All right, now, is it factorable? It's not always factorable. Yeah, that one is. Is this one factorable? Yes, so we don't have to do anything special or freaky. We can just factor it out. So here it is, factor it out. 16 parentheses. What two numbers will give me 16 but add up to negative 10? So t minus 8, t minus 2. And that still equals 0. So now what are my two solutions? 8 and 2. Now can you tell me which one is on the way up and which one is on the way down?
The one on the way up is 2.
The one on the way up is 2. Is 8. Yeah. It has to be, the 2 has to be the one on the way up because the dynamite goes boom, and then you can't tell me that at 8 it's on the way up and at 2 is on the way down because 8 is...
Yeah, because 8 is further along in this.
Yeah. Does that make sense, guys? Okay. Now that I already got this, don't they want my velocity? Yes. I bet I have a 99% feeling that the speed's going to be the same because it's symmetric, right? Like if you have an idea of how motion works, neglecting wind resistance. So here we go. Velocity at 2 equals, and I'm using my velocity equation from up here. So 160.
Oh, because, sorry, you're using 2 because that's it on the way up, right? And
Yes. 160 minus 32 times... Finding my velocity, using my velocity equation.
And the velocity equation was
The derivative of position. So 32 times 2 is 64. 160 minus 64, is that 96? Because 160 minus 60 is 100. So 96, and I need units. Feet per second. Now let's find it at 8. 160 minus 32 times 8. And I bet you it's going to be a negative 96. 160 minus 32 times 8. Yep. Are you shocked that it's negative 96? No, you shouldn't be shocked. It's symmetrical. The time it takes to reach the top is the same time it takes to go from the top to the ground. It took 5 seconds for it to... Okay, I want to make sure that you guys know the whole picture. It took... How long did it take for me to reach the highest? 5. So it's going to take another 5 seconds for it to reach the ground, right? So it takes 10 seconds. This is on the air for 10 seconds. And it's supposed to be symmetrical, like at 256, right? So notice 2 seconds after the blast, boom. And then 2 seconds before it hits ground, boom. 2 seconds before the ground is 8 seconds. Cool or not cool? So you can see it's symmetrical. Right at 2, it's 96 feet per second, and then slows down until you hit the highest. And then right when it's coming back down, right at 8 seconds, it's 96 feet per second. Are we okay right now? Okay. What is the acceleration of the rock at any time t during its flight? Well, the only acceleration that's on this rock is due to gravity. But let's make sure. Take your velocity equation. What's my velocity equation? And we're going to take a what? So I'm going to write A equals V prime, which equals the second derivative of position. So I'm going to put them both there so we can know what we are doing. What's the derivative of negative 32t with respect to t? And I need units. Feet per second per second. You can say feet per second squared.
Okay.
I just don't like it. Because, well, do you guys know what feet per second squared means? I know you guys know, but what about others? It means how much velocity changes per second. So this you can tell. This sometimes you can't tell. You see what I mean? But that's fine. Are you shocked that it's negative 32? No, that's what it is. That's what gravity is. Let's go to the next one. Letter D. When does the rock hit the ground? Well, we know that answer already. It hits the ground 10 seconds. But we want to prove it with math. So if you say that if the S is your position equation, then I want to find where S of t equals what? 0. Does that make sense? So let's prove it with that. So let's write, what's my position equation? You guys tell me. What is it? 160t minus what? And we're going to set that equal to 0. So yeah, you check it out. 160t equals, move the 16t squared to the other side. Divide by, I guess I could have factored out the t right off the bat. Oh well, sorry guys. You know what? Let's do that because that's better math. And it's equaling to 0, so I actually think this is way better than doing that. Factor out a 16t, parenthesis. If you factor out a 16t, then you're going to have 10 minus t. And look, that's way better. Look at this. T equals 0, not shocked. T equals 10, also not shocked.
Oh, okay, because at 0 seconds, it would be... Yeah, okay.
At 0 seconds, you haven't moved. So there it is. We just proved that it takes how long? 10 seconds. Because you're at 0 at 0, the blast hasn't happened. It's about to happen right at 0. And you hit the ground back 10 seconds later. Yes.
Will it always be symmetrical?
As soon as, okay, this is symmetrical because I blasted from ground. But if let's say I'm in a pedestal, or let's say I'm in this table, and I blasted from here, now,
Okay.
yeah, so now that's no longer symmetrical because, I mean, it's going to be symmetrical until you get to this point. But as soon as you reach it, now it's no. Does that make sense? Okay. So it's symmetrical in this case because of my conditions.
And so the velocity will be different. Like the
Yeah, the velocity will be the same when it reaches the same height, whatever this is. But as soon as it passes, like it's going to be different. Yeah. So if I come off a building, it's no longer symmetrical. What's up?
Could you explain why you put S in the
Oh yes, I hit the ground. So here's the ground, and this is S equals 0, and then here's, I don't know, a cannon, and it's blasting. It reaches the height, and then it comes back down. So I want to know when I'm down here. This is S equals 400. So when do they hit the ground? When S is 0. Yeah, position 0. We're okay, guys? All right, let's see what else we got. Example 3. Hey, no one's getting tired. Don't get tired. All right. Let's see. A particle moves along a line so that its position at any time t greater than or equal to 0 is given by the function t squared minus 4t plus 3, where s is measured in meters and t is measured in seconds. Okay, so this time it's not free fall. It's just moving by this function here. Oh, look at this. Find the displacement of the particle during the first 2 seconds. I just want displacement. So how do I find displacement? This is simple, guys. Don't worry.
so you find it at 0 and you find it at 2.
Perfect. Displacement is s of 2 minus s of 0. That's all you're doing. Your position at 2 minus your position at 0. I'm going to come to the other side. I'm going to write s of 0 equals 0 squared minus 4 times 0 plus 3. I get 3. I'm going to go s of 2 equals 2 squared minus 4 times 2 plus 3. And we get, let's see, 2 squared 4. 4 times 2 is 8. So 4 minus 8, negative 4. Negative 4 plus 3, negative 1. Let me know if I make mistakes. I make mistakes all the time, guys. Negative 1 minus 3. My displacement is negative 4, which means at 2 seconds, I am 4 units to the left of where I originally started. And that's true. You started at 3. I ended up at negative 1. That is 4 to the left. Does that make sense?
Wait, could you repeat that part again?
Yes. At position 0 initially, I don't know, pretend this is a number line right here. Let me see. To your reference, okay, so I'm here initially. This is position, position 3. And then I go 1, 2, 3, 4. This position now is negative 1. I was position 3, I'm at negative 1. I'm 4 units to the left of where I started.
Oh, yeah, that makes sense.
Cool or not cool? Cool. Yeah, we can do physics all day. Well, because calculus is pretty much physics, the same thing. Find the average velocity of the particle during the first 4 seconds. Okay. Average velocity, no big deal. Displacement divided by time. That's it. So first 4 seconds, let's see, S of 4. S of 4 equals 4 squared minus 4 times 4 plus 3. S of 0 equals, does everyone know what I'm doing at the moment?
Yeah.
I'm just finding my positions at 4 and at 0. At 0, I already have it. I don't have to calculate it. That was 3. So let's see, 4 squared, 16, 16 minus 16. 3 and 3. Do I move, technically? No. So your average velocity, I'm going to spell it out, average, VEL, equals 3 minus 3 divided by 4, which is 0. And I need units. Do they give me units? Yeah. Meters per second.
Do you need units for the first one?
I guess negative 4 meters. Yeah, if they give you units, you should probably put units. Is everyone okay with how I got 0?
Yes.
Okay. Letter C. Find the instantaneous velocity of the particle when t equals 4. Now I want instantaneous. So what am I going to do? Take the what? Derivative of position. So I'm going to write v of t. I should have put the t in the other one, but that's fine. V of t equals s prime of t, which equals, what's the derivative of t squared? 2t. What's the derivative of 4t? Minus 4, and there it is. What am I plugging in? So now I'm going to write v of 4 equals, and since I already wrote v of t equals s prime of t, you don't have to say s prime of 4, but if you want to, you can. 2 times 4 minus 4. 2 times 4 is 8. 8 minus 4 is 4. And I need units. Meters per second.
Wait, can you explain again the difference between average velocity and instantaneous?
Yes. Instantaneous velocity is at a moment. So I'm finding the velocity right at 4 seconds. And an average velocity is the velocity between the interval 0 and 4. Are we okay so far, guys? All right. Letter D. Find the acceleration of the particle when t equals 4. How do I find acceleration? Derivative of velocity. So I'm going to write a of t equals v prime of t, which equals s prime prime of t, which equals, what's the derivative of 2t minus 4? 2. There it is. I need units. So this is what? Meters per second per second. Or you can write meters per second squared, same thing. But I like the meters per second per second. And I think the math community does as well, because sometimes you'll see free response questions and you'll read it. It'll say the acceleration is 4 meters per second per second. It'll say that in words. So you know that the math community likes that instead of. All right, anyways, letter E. At what values of t does the particle change directions? Okay, direction, we're talking about a vector now. So we need to be looking specifically at what?
When it crosses 0.
Well, when what crosses 0? Velocity. So I need to be looking at the velocity graph. Yes or no?
Yes.
So what is my velocity equation? 2t minus 4. So I'm going to set this equal to 0. And I'm going to solve. 2t equals 4. T equals 2. You guys ready? I'm going to write this particle changes direction at t equals 2, since this is the only time in which velocity changes signs. Does that make sense to you guys? To the left of t equals 2, my velocity was negative. To the right of t equals 2, the velocity turns positive.
Because it crosses 0.
Because the velocity graph crosses 0. Yeah, but notice that we didn't show the graph. But we okay. Yes, 2 times 2 is 4. 4 minus 4 is 0. Right?
Yeah.
The particle changes direction at t equals 2 seconds, since this is the only time in which velocity changes signs. And I don't know what my domain was, if the domain was t greater than or equal to 0. So if you wanted to, you could say between 0 and 2, you're moving to the left. And between 2 and infinity, you're moving right. Yes. If my velocity is going to change signs, it's going to happen if I cross the x-axis, which is 0, velocity 0, right? So I equal it to 0 to see if there's, and these are candidates. These are, it's a linear one, so it's for sure going to cross. How do we feel, guys? Okay. So we have an activity. You can't do it all. We're going to do some of it together.